Okay, Laura, it's Melissa. I think we'll go ahead and get started, okay?
Sounds good.
Sounds good. Okay, great. Well, welcome everyone to our webinar today, Climate Change Vulnerability Assessments and Green Infrastructure Initiatives to Enhance Stormwater Management and Watershed Planning. This is part of our Integrated Water Management webinar series. My name is Melissa Soline. I'm a Program Manager for the Great Lakes and St. Lawrence Cities Initiative. I also have on the line with me Laura Bretham from our Chicago office managing the webinar from the technical perspective today. Before we launch into the webinar, I'd like to first just go over some housekeeping things. First of all, the webinar is being recorded and will be posted on our website afterwards for your reference. Secondly, all lines of participants will be muted during the presentation portion of the webinar. We will have a Q&A opportunity at the end of the webinar, at which point we can take questions from participants. In order to ask a question during the Q&A session, you can type your question in the chat box, which you'll find on the right-hand side of your screen on your webinar dashboard. Or you could raise your hand by clicking the hand icon, again, on the dashboard on the right-hand side of your screen. And at the appropriate time, we can unmute your phone line so you can ask your question. Feel free to send us your chat questions throughout the webinar, as the presentations are going on. Laura will be collecting them so that we can read them back to the panelists during the question and answer session. And if you happen to have any technical problems during the webinar, please feel free to email me. My email is up on the agenda, which you should see on your screen right now. I'll be monitoring my email and can try and help you out during the webinar. So with that, welcome again to today's webinar. I've really been looking forward to this one because it's an opportunity to showcase some of the great work that's being done in a few of our member cities on the issues of flooding and other significant climate change impacts that cities are facing. We were fortunate to receive an RBC Blue Water Project grant to support 2 demonstration projects that work to integrate urban stormwater management, watershed planning, and information on climate impacts. So we'll hear today from the City of Hamilton on their Spencer Creek Climate Change Vulnerability Pilot Project, as well as the City of Thunder Bay on their Memorial Avenue Low Impact Development Project. Our hope with projects like these and through our Municipal Adaptation and Resilience Service, which we've coined MARS, is to help cities find ways to better protect our urban waterways, the lakes, our rivers and tributaries, our municipal infrastructure, and of course the citizens of our cities in the face of more intense weather in the region and other climatic impacts. I think these 2 projects that we'll be hearing about today are really good examples of how we can better integrate planning around climate change and implementing measures like green infrastructure. So with that, I'm going to let the folks that are actually doing all the work on the ground present on their projects. We'll be starting with the City of Hamilton. I'm pleased to introduce Brian Hindley. He's with Matrix Solutions. He's part of the Hamilton project team working on the Spencer Creek project. And so with that, I'll ask Laura to hand presentation controls over to Brian, and we'll turn it over to Brian. And Brian, you may have your phone on mute.
I'm here.
Oh, there you are. Yep, we hear you loud and clear.
So I'm just hopefully I have this up on the screen. No?
Yep, your presentation is up and you're ready to go.
Perfect. Well, thanks, Melissa. We're really happy to be part of this today. And I just want to acknowledge the City of Hamilton, the Hamilton Conservation Authority, and the Great Lakes St. Lawrence Cities Initiative as kind of the partners in this, and of course the RBC Blue Water Project. So our topic is to look at environmental and infrastructure vulnerabilities from climate change in a watershed that's within the City of Hamilton. And my co-contributors, I guess, are Nahad and John from the city and the Hamilton Conservation Authority. So there's been a growing public awareness of extreme events in Ontario, as there has been elsewhere. So, for example, we've had 4 extreme events in 6 years in the city of Hamilton. And as you can see, a number of extreme events in other parts of Ontario in as little as 2 weeks, for example, in Newmarket. And since 1995, we've had some sort of state of emergency somewhere in Ontario every year. I think the significance of this is not just the public awareness, but the fact that there's a growing amount of municipal budgets that are devoted now to dealing with some of these infrastructure issues. So these are just the RBC Blue Water project goals, so looking at increasing our knowledge and awareness of sustainable water management. And in this project, considering issues such as flood damage reduction, stormwater runoff, improved water quality, and increased awareness of urban water management. For this particular project, we have a number of technical tasks. So we were looking at evaluating and selecting a number of different climate change models to consider here, and use the output from those models to assess the vulnerability of some environmental features in our project Watershed, and also infrastructure features as a result of these climate changes. And in addition to looking at the output from climate models, we've taken those outputs and used them in doing more detailed hydrologic and hydraulic modeling of some of these future climates to kind of drill down and look in more detail at how some of these changes may affect the infrastructure and environmental features. So our study approach is to look at a number of these models, compare and contrast their strengths and weaknesses, develop or generate a series of environmental indicators that relate to temperature and precipitation change, and then downscale or create more detail in terms of looking at how these future values can be used in hydrologic and hydraulic models to look at more specific changes. As part of doing that, we've generated then a series of future flood flows and stream characteristics that are indicative of threats to the watershed, the infrastructure, and environmental features, and developed finally some adaptation recommendations as to how municipal and conservation authority policy and planning might be adjusted to accommodate some of these findings. So to give you a bit of perspective, our study area is the city of Hamilton, which is at the western end of Lake Ontario. The city has a population of about 500,000 people, and the greater Golden Horseshoe area, which basically runs from Toronto around the lake to Niagara, is over 8 million people. So we have a large population base that's within this area. And the red line here is the Spencer Creek Watershed, which is the area or study focus for our project. So the Spencer Creek Watershed is really typical of many southern Ontario watersheds in that it has a mix of both urban and rural land uses. Urban land uses constitute about a third of the basin, and they tend to be concentrated down near the mouth of the tributary where it enters Lake Ontario. And I think in addition to the human land uses, we have also a mosaic of natural features. So there are some large blocks of natural features and then a number of different smaller fragments. And many other watersheds in southern Ontario have this kind of general characteristic. The drainage basin is about 230 square kilometers or 92 square miles. It's, as I mentioned, primarily rural headwaters and urban lower reaches. So the environmental features that we wanted to look at are some of these large blocks of habitat. And so we have 2 wetland features, the Fletcher's Creek wetland and coldwater stream in the headwaters, the Beverly Swamp, which is a little bit further downstream, the Christie Reservoir, which is a small reservoir within the watershed, and then the Dundas Valley forests, which are closer to the mouth. So each of these features has some unique aspects of it that have potential to be impacted by climate change. The Beverly Swamp is about a 2,300 hectare wetland, so that's about 5,000 acres. It has a very high quality forest swamp feature, which includes fairly rare Carolinian vegetation, typical of only a few locations in southern Ontario, and it provides significant base flow and water storage functions to the watershed. There also are a number of rare species of birds, plants, and amphibians. The Fletcher's Creek wetland is about 1,000 hectares or 2,200 acres of wetland, and it provides or includes a number of different wetland types such as bogs, fens, and swamps. Also important is that it's connected to a cold water stream that supports brook trout, and these streams are fairly rare or becoming rare in Ontario. In addition, there are already some threats from invasive species. The Christie Reservoir is a small reservoir typical of many online multifunction reservoirs in southern Ontario, and these reservoirs have the challenge of trying to balance upstream and downstream water management objectives, so flood control and low flow augmentation in the downstream area, while at the same time maintaining recreation and providing spawning habitat and winter refuge for fish in the reservoir itself. The Dundas Valley Forest is a 1,200 hectare or 2,500 acre Carolinian forest in the escarpment area, so the slopes of the escarpment near the lower part of the Spencer Creek watershed. It also has rare Carolinian vegetation and supports habitat for a number of forest birds, and most importantly the rare Jefferson salamander, which survives in or reproduces in ephemeral swamps in the forest area. It also supports cold water streams. In terms of infrastructure, we focused our work on looking at 14 bridge crossings within the lower Spencer Creek, and here are some examples of 3 of them, ranging from the upper part of the lower Spencer down to the mouth. And I think the important point here is that not only do we have bridge structures that may be affected by changes in stream flows and storm events from climate change, but they also have associated infrastructure. So many of these features have water mains or trunk sewers or gas and hydro lines associated with them, or even fiber optic lines. So an impact to the bridge can mean a lot more than just an impact on transportation. And also, as you can see, some of these structures have their piers within the riverbank or within the stream itself, and these structures can be susceptible to erosion. So any changes in the stability of the stream or erosion can impact on the structure. So to talk a little bit about some results, we're just really getting into the results at this point, but I thought we could share a few things that we've observed at this point. So when we look at future climate projections, we generally want to look at several different models to generate these results, as each model has strengths and weaknesses. And in fact, there can be quite a bit of data variability in the output of these models, and that can cause some uncertainty in terms of the results. So it's very important not to think that any one model is going to give you the right answers, but rather you need to look at several of them to better understand what's going on. And most importantly, I think there's a significant role for expert judgment in analyzing the results of the models, because they're not really giving you absolute results, but they're giving you ranges. And so one of the things we tend to look at is analyzing the trends and not the absolutes in terms of the model outputs. And I think the importance, or one of the important characteristics of using these models, is their potential to influence current planning and policy, because particularly in water management, a lot of the current policy and planning tends to be based on analysis of past trends as opposed to future ones. So when we look at these climate data sets that are generated by the climate models, we need to keep in mind that in fact they're predicted values, they're not absolute data. So the standard practice here is to look at multiple models and look at the strengths and weaknesses of each, and to recognize that there is uncertainty in the results. So these are just some examples of a whole range of models that were analyzed, and you can see that there's considerable variation in both the projected precipitation values and the projected temperature values. And these depend basically on global climate factors, as well as looking at different carbon emission standards for the future. So that's part of what creates a lot of the variability here. Secondly, I think when you then take this data and downscale it to be used in hydrologic and hydraulic models, we're basically taking data that's developed as kind of daily output data and turning it into hourly data. And there's a tendency to perhaps think that this gives you, or the tendency is that you kind of have a false sense of security about your data. So we have to be careful to recognize that when we're adapting this output to hydrologic models, we need to consider that there still is some inherent variability. So when we look at these projections, I think while there is uncertainty in the output that's generated, we can generally consider that we have more confidence in some of the longer-term trends in precipitation and temperature, and less certainty in some of the short-term trends. So when we look historically at some flood events in the province, for example, if we look at the far distant past, we often find that many of the storm events were generated, occurred as long-duration storms. So, for example, Hurricane Hazel occurred over a number of days. But when we look at the more recent trends, a lot of the storms that were generated tend to be much higher in intensity and shorter in duration. And we have less confidence in the climate models and being able to predict how those effects might change. So when we look at effects or preliminary results in relation to infrastructure, we can see here an example of a number of different outputs that were generated from the hydrologic hydraulic model. And these are time series flows that show the return frequency or the magnitude of different return frequency flows. And I think basically what we see here is that while there's a difference in the actual absolute outputs from the various models and the various future time periods, there is a consistent trend. And so we do see that there are increases in the magnitude of events, and generally speaking, the more frequent events seem to show a greater change in magnitude. But I think what's important here is that it's not just the fact that future storms may get larger, but in fact that these infrequent storms will occur more frequently. And that's sort of borne out by some of the recent events that we've seen. To look at this another way, we compared the results from one of the climate models that were downscaled and used in the hydrology model, and looked at how these time series flows changed in comparison to existing conditions. So the existing conditions are basically looking at the historic flow regime and developing the current time series of flows, so the magnitude of the 2, 5, 10, and 25-year flow, and comparing that to the future in 3 different intervals, sort of a near, mid, and far future interval, if you want. And so again, what we see is that there is consistency in the trends here. There is some increase in the magnitude, but again, if you look at this and look at how the existing 2 or 5 year flow would look in terms of some of these future predictions, those events or the size of those events would occur with greater frequency. So one of the things we looked at was that we recognized that some of the more frequent flows may change more so than some of the less frequent flows, and generally speaking, stream erosion is impacted by these frequent flows. So what this means is that we could have greater threats to aquatic habitats as erosion thresholds change in the channel. We can have less stability in the stream channel, and this tendency for increased channel instability could also then have impacts on some of the bridge substructures. So that's kind of the nature of the pathway of effect, I guess, that we need to look at. And of course, if these threats were to continue, then they may appear to be subtle changes at first, but they could lead to larger scale effects, such as this erosion failure here. Looking at some of the environmental feature results, we do see some trends in terms of increasing mean annual temperatures, increases in the maximum temperatures, less cold weather as evidenced by the fewer days that are below a cold threshold, and increases in the number of growing season days. And all of these factors come into play in looking at how the form and function of some of our environmental features might change. In terms of precipitation, we see that there are increases in total precipitation, more days with significant precipitation, and some increases in some of the longer duration storm events. Looking now more at the output from the hydrologic model, and considering, for example, the water budgets of these wetland and forest features, we will see or do see an increase in the evapotranspiration. So what this means is that there is more water loss from these wetland and forest features. And this is most significant in the summertime, but I think the other thing that's worth noting here is that there is still some increases in evapotranspiration in the shoulder seasons, in the spring and the fall. So these in total can have a cumulative effect on some of the wetlands. This is a graph of accumulated snowpack, and the message here is that there is likely to be less accumulated snowpack over the winter, which translates into less of a spring peak in terms of snowmelt, which may have impacts both on flooding and also on the habitats for some of the spring reproducing amphibians, for example. And the other thing that this tells us is that it's likely that we're going to have more rainfall than snowfall in winter. So the potential again for more runoff through the winter as opposed to in a peak in the spring. And this can be shown to some extent by looking at the annual stream flow. So essentially the changes in stream flow seem to be a change in the distribution of stream flow throughout the year when we look at monthly stream flows. So looking at this graph, for example, we see if the blue line, which is existing conditions, shows a fairly pronounced peak of flow within the month of April. When we look at the future climate scenarios, we tend to see more of a gradual runoff throughout the winter. And then in addition, although we see more stream flow perhaps through the summer months shown by this graph, we need to look at this a little bit more carefully, because it may be in fact that what we're seeing is more event-related flows. So what we might actually be seeing here is the effect of more events, but not necessarily more base flow in the stream. So that's the easy part, but what does all this mean? So just in terms of the wetlands, what this can mean then is that we may have increasing potential threats to brook trout habitat from thermal effects. We may have more potential for in-stream erosion, and some of the changes in snowpack and also evapotranspiration could lead to an expansion of invasive wetland species if the water levels in the wetland are lowered. So Beverly Swamp, again, the same sort of trend. One of the things here, because it's such a large feature, is that there may be a potential loss of the water storage function of the swamp, which is important in terms of spring runoff and attenuating event flows. With respect to the Christie Reservoir, we can expect more unpredictability in water management. Many of these reservoirs are operated with manual control structures, so the ability to respond is slower. So things like less snowpack and a more drawn-out winter runoff could mean that it would be more difficult to ensure that there's enough storage retained for base flow augmentation in the summer, and more highly variable spring reservoir levels, which could threaten fish spawning. In the Dundas Forest, one of the key concerns here are the threats to vernal pools and amphibian habitat. So if we don't have that more extreme spring peak runoff, we may not get the water filling some of these ephemeral pools in the spring that are used for reproduction. With respect to infrastructure, the increase in erosion may potentially threaten some of the stability of the channel or the bridge substructures. The increased frequency of floods represent potential threats to flooding on roads or the bridge conveyance capacity, and the concern with respect to associated infrastructure. And there are potential changes to creek hydrology and hydraulics. So what actions would we take? We've just started to develop kind of a laundry list of things to look at. So for the environmental features, things like enhanced monitoring, restoration planning, what types of species to plant, policies and planning tools that would protect environmental features, and looking, for example, at more specific species management plans. With respect to infrastructure, we might be looking at redefining acceptable risks, enhanced monitoring, looking more at emergency response, perhaps design guidelines in relation to infrastructure, more attention to operations and maintenance and flood protection, and finally weather and rainfall forecast. So finally, I just want to acknowledge our partners again, and also note that we did get some additional support through McMaster University and the Ontario Climate Consortium. So thanks very much. I guess I can turn it back to you, Melissa.
Great, thank you, Brian. Laura will transfer controls now, I think, over to Brad from the City of Thunder Bay. I'm happy to introduce Brad and his team. They'll be presenting on their work on a low-impact development project they've got going on within the City of Thunder Bay. Brad, I think we've got your presentation up, and turning it over to you.
Great, thanks, Melissa. Good morning, folks. My name is Brad Doff. I'm the City of Thunder Bay's Acting Sustainability Coordinator, and it's a pleasure to be here with you all today. As we begin, I'm joined by a great team of folks here around the boardroom who will be giving a presentation. There's 3 others here, and we're entitling this presentation, LID, A Tale of Two Sites. For those of you who don't know what LID is, low impact development, I'll be explaining that in a few moments. But those presenting with me this morning, we have Werner Schwar here, who's a parks planner for the Parks Division here. We have Gail Willis, a senior technologist in engineering, and Lee Amelia, who's our urban forest program specialist, Parks Division, is with us, and they all bring different levels of expertise to this project, and so we felt it would be important just to have everyone have a few minutes here to pitch in their expertise. So, as you may be aware, we received funding through the RBC Blue Water Project through the city's initiative to contribute towards the installation this spring of a new low-impact development on Memorial Avenue in Thunder Bay. And so in today's talk, we're going to mostly focus on this new site, which is on the right here of your screen. But we also wanted to capitalize on the comparison between this site and an LID site that was installed, pretty much about 50 meters away. That was completed in 2013. And look at the lessons learned. And in a nutshell, as we begin here, I'm going to let the cat out of the bag. Both sites were prescribed the same type of LID design, but in the end required 2 distinct systems or designs given the change in the site characteristics between these 2 sites. So today, the objective is we just wanted to provide an overview of the intent of the RBC project. We wanted to talk a little bit more about the lessons learned and regarding these 2 LID projects and how this can inform other municipalities in their planning. And then the third thing we wanted to cover is just the next steps for this RBC-funded project and a chance to see some of the technical details behind the scenes. So as I introduce the players involved in this project, I wanted to preface this slide by talking a little bit about the current city structure, because I think it's important. Right now in Thunder Bay, there's no one division responsible for stormwater management and LID development at the moment. And so an ad hoc team in 2012 from a number of us was set up from staff level with permission of the senior management to explore more opportunities for low impact development installations and to educate ourselves internally before we would expect our contractors to start building them. So what's exciting is that in the near future we are anticipating a new division who will be focusing solely on LID and stormwater management in the near future. So our team members consist of about 8 city staff, all from various sections of the city: Earth Care Thunder Bay, our engineering and environment and parks division, and realty services. Only some are here represented today in this presentation. And our partners, we're grateful for the support and leadership of this project from the city's initiative, the funding coming through them and RBC, and Emmons and Oliver Resources, collaborative group of environmental and design professionals. They've been retained to work on our stormwater master plan here at the city, have been involved in the design of one of the projects, and then Earth Care Thunder Bay as well. It's a formalized partnership between the city and the community that works towards sustainability, greenhouse gas emission reductions, and climate adaptation. So these were the partners to have on board, and a wonderful set of expertise. So the intent of this RBC project was we really wanted to work towards improving the quality of stormwater discharged into Lake Superior, and this particular area along Memorial Avenue is particularly prone for stormwater issues. We wanted to focus on reducing peak flow and the volume of stormwater runoff. We also wanted to look at how we could integrate trees and shrubs into the design to increase our urban forest canopy. And as it relates to that, this sits along one of our Memorial Avenue image route, which is one of 3 feature corridors in the city. We wanted to increase the aesthetics along this avenue. We wanted to look at integrating LID into educational campaigns to promote the use of green infrastructure throughout the city of Thunder Bay. And then as it relates to climate change and adaptation, we wanted to definitely use this as a means of increasing our resiliency to climate change and use that as a driver for this project. And as it relates to climate change, and as what Brian was mentioning earlier, 2 of the major impacts that we're going to see here as it relates to stormwater in Thunder Bay are warmer water, and heavy rain events. And as water warms, we're going to continue to see a decrease in cold water aquatic habitat. We'll see more algae blooms and beach closures and invasive species. Some of the impacts related to heavy rain events, there's water quality issues, there's increase in urban flooding, and of course the water quality issues as it relates to combined sewer overflows, which Thunder Bay still has a small percentage of them. So we realize that managing of stormwater, especially with respect to low-impact development, will play a vital role in adapting to the climate change impacts we'll be facing in the future. So those of you who may not be familiar with low-impact development, essentially it's a land planning and engineering design approach to manage stormwater runoff. And really it's an emphasis on conservation and a use of natural site features to protect water quality and really reduce the quantity of runoff and the velocity of runoff. The model LID really only works through a decentralized model, so that means we have a lot of small facilities installed all throughout the neighborhood or city, and they are to replicate the pre-development watershed. And although this is a fairly innovative approach, and it's been adopted as a best management practice across Canada and the U.S. It's a relatively new concept here in the city, and so we're excited to continue to move this agenda forward in sustainable stormwater management in Thunder Bay. And just as it relates to the definition, LID's principle, as you can see here on the left, will allow a developed site, like our typical Thunder Bay arterial, to maintain its pre-development watershed and ecological function, as we see here on the right. And so that's the goal. We're trying to treat the water droplet or the raindrop as close to the source as possible. These do include different interventions like our bioretention facilities and vegetative swales, as we see here, or rain gardens you may be familiar with. Just to keep things going and to give you some perspective, where are we located? Thunder Bay is northwestern edge of Lake Superior, and we're within the Lakehead sub-watershed, or the Great Lakes watershed, of course, and as you can see here on the right, it's a fairly large watershed, approximately 9,000 square kilometers, but the city itself is approximately only about 4% of that watershed, so about 300 square kilometers. And where is our project within the city itself? We are located, the site is located within the urban area of the city in the north end of intercity area, and it's a flat, poorly drained area which used to be muskeg, and I don't think it gets any better than that for an ideal place for an LID site. And so on the right-hand side here you can see this new memorial LED project is slotted for installation this spring, and this site essentially drains directly into Lake Superior through a combination of storm sewers and engineered channels, concrete channels and ditches. So it's a very important site. I'm going to pass things over to Werner now for continuing on in this presentation.
All right, so I'm going to be talking about the differences between the past project that Brad was mentioning a few years ago, called the Beverly LID site on the left, and our new Memorial LID site on the right. That Beverly site was really our first foray into a true LID, and was done all in-house, myself being a landscape architect, Gail handling the engineering, and we did that through just our own knowledge, and the project worked out reasonably well. This other site, Memorial, we thought, well, we did it 50 meters away. What could be the problem doing it again on the other side? And lo and behold, when we actually got into the project, there were a whole lot of differences that made the design required to be quite different. So even though they're really close together. These are two existing condition shots. The Beverly Street side was actually more of an upland site, although the picture doesn't show it very well. It was a fill situation, bermed about 1 to 2 meters tall, whereas our site on Memorial is low and depressed, adjacent to a parking lot, and has lots of standing water issues currently. When we got into the design process, again, like I said, we had 50 meters of difference, but we had a great deal of difference in the actual sites. So in terms of groundwater table, the Beverly site was 2 to 3 meters below the existing grade, while in Memorial we were less than a meter. So the new site, Memorial, wasn't deemed suitable for infiltration like the other site was. So we had to change the scope of our project and investigate other LID types. The soil itself was different. The Beverly site was dry coarse fill material, and once we get into the Memorial site, the soil sample indicated silt and musket. So again, not as suitable for infiltration. The topography, again, was different. We had a hill situation on one versus a low wet area on the other. So the positive was we required less excavation, but we needed much more detailed grading and soil investigations to make something work. Utilities, we had a clear site on the Beverly Street side on the left, but we actually have two 600 mil diameter storm sewers going right through the middle of this site, and they're close to the surface, which again posed a very significant design constraint when we got into things like excavation and cover of pipe. A couple final more differences was pedestrian and circulation around the site. On the Beverly Street side, again, we had adjacent sidewalks, but no one ever passed through the site. On the Memorial site, we have adjacent sidewalks as well, but we have a lot of desire lines from people wanting to go from the main street to businesses rather than cutting across driveways. We had to accommodate that. And finally, visibility of the site. Although they're both adjacent to the main street, the one site is adjacent to businesses and a highly used entranceway, so the site becomes much more visible and thus much more significant for what the public's going to think about it afterwards. And also required consultation with the business owners, which we did not need in the other site because it was a public park. I'll hand it over to Gail now, who's going to talk a little bit more about the engineering.
Thanks, Warner. This slide shows the drainage area for each of the LID sites. On the left is the Beverly Street LID that we constructed in 2013, and it is shown in gray. The area draining the site is approximately 0.2 hectares and is mainly road runoff and is shown as the lined hatch. This is the actual drainage area physically getting to the LID. An additional 2.5 hectares could be drained to the site from the north of Beverly Street, but there is an existing sidewalk which acts as a barrier and prevents runoff from the north. So the total potential drainage area to the Beverly Street site is approximately 2.7 hectares, and the facility has been designed for this potential drainage area. On the right is the Memorial LID site, shown in gray, which will be constructed in May of this year. Similar to the Beverly Street LID, there are two catchment areas draining to the site. The drainage area shown as the lined hatch is approximately 0.4 hectares and includes a portion of the commercial buildings and parking areas. An additional 0.2 hectares could be drained to the Memorial LID site from the northeast for a total potential drainage area of 0.6 hectares. The Memorial LID facility has been designed for the potential area of 0.6 hectares. One element that these two sites share is the storm sewer outlet. The existing storm sewer bypasses the Beverly Street LID and then bisects the Memorial Street LID downstream. An existing storm sewer is located between the Beverly Street cul-de-sac and the Beverly LID site to the north. Continuing downstream, the storm sewer connects to the existing manhole on the east side of High Street and picks up stormwater from High Street. And from there, two parallel storm sewers continue across Memorial Street and bisect through the Memorial LID site. The Memorial site has been designed as a two-cell bioretention filtration system where each cell outlets to one of the storm sewers. Ultimately, both LID sites drain to Lake Superior through the existing storm sewer system, outletting to a downstream concrete channel and discharging directly to Lake Superior. In this slide, we are showing the two LID sites in more detail. Both facilities accept stormwater runoff from direct impervious areas. However, flow to the Beverly Street is channeled along Beverly Street by the existing curb and gutter in a traditional manner, and flow to the Memorial Street LID is conveyed over the parking lot surface by sheet flow. Now, the ways that these two LID sites accept stormwater runoff are similar. Both were designed to have curb cuts, and stormwater would enter the facilities into a pre-treatment area. However, the way the pre-treatment areas have been designed are different. For the Beverly Street LID, we removed approximately 15 meters of the existing curb and gutter and replaced it with new curb and gutter with curb depressions to allow flow from the roadway to enter the pre-treatment area. The pre-treatment area is where most of the road gravel from winter maintenance and any other materials contained in the runoff will drop out. A rock weir separates the pre-treatment area from the bioretention facility, and the bioretention area consists of engineering soil mix, pea gravel, and washed stone, and stormwater is filtered through these layers. Any water that has not infiltrated through the native soil is collected through a subdrain system, ultimately discharging to the existing storm sewer to the south. On the other hand, the Memorial Street LID, stormwater is conveyed to the site by sheet flow from the existing parking lot. Some of the challenges of this site are the proximity of the existing surface to the groundwater table and the two storm sewers that divide the site. The storm sewers are very shallow, and in some locations, particularly in the parking lot, you can see the top of the sewers from the surface. So the design of the site used this feature as a physical barrier to divide the LID site into two biofiltration cells, as well as a potential trail connection through the site from Memorial Street. To direct the flow into the new site, a new curb and gutter will be constructed at the edge of the existing asphalt, which will direct flow to two pre-treatment inlets, one for the north biofiltration cell and one for the south. The pre-treatment inlets direct runoff into a concrete runnel with clear stone weirs situated on each side of the runnel. A runnel is basically a shallow concrete channel at a slight grade to allow gravel material to drop out into the channel for easy maintenance. From the runnel, water spills into the biofiltration cells. Each cell consists of engineered soil mix and a sand filter with a subdrain that is situated along the west side of each cell. The subdrain connects to outlet pipes that will be constructed with duckbill valves to prevent backwater from entering the facility. To construct the Beverly Bioretention LID facility, we excavated over 600 cubic meters of native soil. This was due to the area between Beverly Street and the cul-de-sac. It was essentially a rounded mound that was left there and sodded during improvements to Beverly Street and High Street in the early 1980s. Groundwater was seen during excavation and approximately 2 meters below the original ground elevation. The excavation was then backfilled with a layer of washed clear stone, and we placed a perforated subdrain on top of the first lift of stone. For the next layer, we placed pea gravel, and over the pea gravel, we placed a non-woven geotextile to separate the stone from the engineered soil mix. The soil mix that was placed was a mix of 85% sand and 10% silt and clay and 5% organic matter. Then we spread a special bioretention seed mix over the soil with an erosion control blanket, which held the seed mix in place while it germinated and took root. The Memorial Biofiltration LID facility is situated about a half a meter lower than Memorial Avenue, and the groundwater elevation is about half a meter below the existing ground of the site. So for this reason, the Memorial LID facility was designed as a filtration system, which would include more plants and shrubs to filter and clean stormwater runoff. We plan to excavate approximately 275 cubic meters of the native soil and replace it with a soil mix consisting of 90% wash sand and 10% compost. The sand filter along the west side of the facility that you can see in the bottom will have the same soil mix and will be covered with clear stone to protect the integrity of the filter. Now I'm going to pass it over to Warner, who's going to explain some of the plant material.
Thanks, Gail. So continuing on our differences of the two sites, again, our Beverly Street existing park, we wanted to keep it much more park-like, so majority of trees, shrubs, and just sort of grass and herbaceous material that would retain that open look, park-like quality. Whereas in the Memorial site, it was much more contained by roadways and the parking areas, but also adjacent to the business. And one of the main businesses adjacent to this site is a hunting and fishing store. So we thought it would actually be quite interesting to have the plant material be much more native and reflective, give that business an interesting foreground. So the planting design was much different in that instead of grass and seed mix, it will all be trees, shrubs, and native herbaceous material. Trees such as the tamarack, shrubs such as dwarf bush honeysuckle and dogwood, and range of herbaceous from wet material like iris to dry material like yarrow. So the difference being in the Memorial site, we have both wetland in the bioretention areas, but then in where the sand filter is, they would need dry species. Whereas in the Beverly site, pretty much a more homogeneous planting was acceptable. And this alone presents much more design challenges, having these different types of planting in a small area, but recognizing that it has to also look good for the business's perspective rather than just function as a stormwater amenity. And I'll pass it over to Lee now to talk about our lessons and budgets.
So first I'll speak to some of the cost factors associated with our LIDs. As you can see, the estimated cost for Beverly LID was almost double that of what was actually spent. The majority of our Beverly cost savings ended up coming from internal staff helping with the design, administration, and construction of the facility. The original estimate was based on tendering out the entire project to one single contractor, which wasn't necessary in the end. We hope to realize similar cost savings with the Memorial LID site through similar commitments from city staff. Regarding our external funding sources, CN Eco Connections contributed to our Beverly site, while RBC Blue Water contributed to the Memorial site. And it's noteworthy that these projects likely would have never gotten off the ground without external funding. Here you can see a comparison of the actual costs from Beverly and the estimated costs from Memorial. Percentage-wise, you can see the largest expense for Beverly went towards greening and construction, whereas the Memorial LID shows materials as the largest cost. But this was also the case for the estimated cost at Beverly. We were able to save a significant amount on materials and hope to do the same at Memorial. Memorial will rely more heavily on filtering stormwater in a tighter space, so our costs for additional concrete formations, drain tile, and special engineered soil will increase our material costs for this site compared to those for Beverly. I'll now run through some of our lessons learned and next steps regarding design, construction, in-house experience, financial challenges, and education. And as you can see on the right-hand side, we have an image of the final Beverly Street LID.
Successful LIDs require the teamwork of experts from several disciplines. Our internal LID team has learned that every location is unique and there's no cookie cutter or one-size-fits-all designs when it comes to implementing these facilities. Our two comparison sites are 50 meters apart and required completely different LID approaches. Every LID site will have its own unique characteristics and require people to think outside the box and work together. Ongoing training and development for internal staff is required, since these designs are fairly new to Thunder Bay. They will take time to perfect, especially in relation to our city's present infrastructure and climatic challenges. We've also learned that site analysis prior to design is important before committing to any specific location. Our internal engineering field staff mapped out all the curved lines for the Beverly facility, while the sewer and water crew did all the excavations according to the design specs, with on-site supervision from our technical engineer. This is not a typical workday for the city crews who normally install and maintain sewer and water connections and build straight roads. Being involved in these projects and learning about LID concepts is an excellent opportunity for internal city staff, which will help us save costs down the road. While we understand that gray infrastructure is necessary to manage urban stormwater, LID and green infrastructure is demonstrating an alternative infrastructure that can improve the quality of water being discharged into our lakes and streams, while filling the void left by traditional engineering, which generally lacks greenery at surface level that can make cities a more beautiful place to live. The greening component of LID enhances people's quality of life in urban environments and is helping our city meet some of our beautification and climate adaptation goals alongside stormwater management. Local contractors are preparing our engineered soil media, seed mixtures, greening, and concrete formations, so it's important to keep them closely involved, since we'll likely need to outsource the construction of these sites when our internal resources become unavailable in the future. So who is responsible for low-impact developments? Is it parks, realty, roads, engineering, or environment? We found it can be a challenge to finance the capital costs of LID sites as well as the maintenance costs, since there is presently no money in the city budget allotted specifically to LID facilities. Hopefully this will change once the Stormwater Master Plan for Thunder Bay is released later this year and we can really pinpoint the best bang for our buck locations and start implementing LID on a wider scale. For now, we'll rely on internal staff with the technical skills and equipment to respond to the general maintenance of these facilities. We do need to continue educating the public and businesses on the benefits of LID infrastructure and the promotional opportunities that can exist. Volunteer engagement is also important to build the connection between LIDs and community spaces. Educational signage provides ongoing education for the facility design and the benefits of LID, and media events after construction will help provide awareness to the general public. And that wraps up our presentation. I've left our contact information on the last page here. I want to thank the whole Thunder Bay team here and Great Lakes St. Lawrence City's Initiative for having us today. I'll pass it back over to Melissa.
Great, thank you so much. I realize we're at the top of the hour, but I wanted to make sure these great projects had a chance to be presented. There's a lot of great work being done. We're going to go ahead, Laura. Can you handle questions that have come in via the chat, and then we'll handle hand-raised questions as well.
Great.
And sorry, Laura, my phone is about to die. If you don't mind wrapping up too as well.
Sure, no problem.
I lose you. Okay, thanks.
So we have two questions from Brian Hindley's presentation. The first is from Mayor John Dickert of Racine, Wisconsin, wondering about, with the bridge infrastructure, if you're doing anything for stream bank protection from erosion. I know you talked a little bit about erosion being an issue there, Brian.
Okay, I think, I think what we would be doing is looking at the extent to which we might have to do things like accelerate programs to investigate stream bank erosion and undertake works. Our project is really looking at how some of the existing programs might need to be adapted, I guess, more to considering these things. But I think one of the important things is, perhaps in increasing monitoring of these types of situations to get a better handle on the rate of erosion and what's occurring.
Great. So the second question is from Jeffrey Smith, wondering about the high flow events and the frequency of those, and why are these high flow events still referred to as 2-year or 25-year events when they may be happening much more frequently, and if there's any work being done to update those thresholds?
Well, again, I think that's probably an outcome of our project to look at first of all how these events may change. But I think, as I mentioned, it is as Jeff's indicating that there's an increase in the frequency of these events. So it really becomes first identifying what those changes are and then deciding whether or not things like design standards for bridges and so on should be changed to reflect either the frequency of the 2 or 5 year storm or the magnitude, or perhaps generating new design storms. So I think we're a ways away from actually answering those questions, but I think we're hopefully going to shed some light on them.
Great. Thanks, Brian.
Thank you. Sorry, Laura, I'm back on.
Oh, great. We have one more
question. Great. Okay.
Yep. This is from John Velick for the Thunder Bay team, I think, or for both. What kind of maintenance or clean-out is required for bioretention and biofiltration facilities, and what would the filtration media require in terms of excavation and replacement?
This is Werner. I can answer that a little bit. The primary maintenance is at the pre-treatment area, so the winter sand and salt is really the big concern that you don't want to get into the filter medium. So that's why in the case of Memorial, the concrete runnels were designed there to make it easy for that to be shoveled out every spring. Other things like how the winter maintenance itself is handled is important to consider. For example, how the snow plowing regime happens so that you're not dumping all the piles of sand-ridden snow right on top of your inlet in the LID. So the answer to that is not simple. It's almost the whole way things are maintained and operated has to be looked at depending on the individual LID.
Great, thank you. Laura, any questions by folks raising hands?
I don't see any, no.
Okay, great. And no other chat questions at this point?
Correct.
Okay, great. Well, I'd just like to thank everyone again for joining us and for hanging on there a few minutes over the 11 o'clock hour here in Chicago. I've listed my contact information. If folks do have any additional questions for our panelists, please feel free to send them to me, and I'll get them to the right person, and we'll get you an email contact so that you can get your questions answered. I wanted to also alert folks that our Integrated Water Management webinar series is going to take a break over the summer months. We'll be back in September with a webinar to explore some interesting work being done by the Environmental Law Institute. They're helping municipalities achieve habitat benefits and build resilience through acquiring buyout properties within their jurisdiction. So that should be proved to be an interesting session. In the meantime, we've got our web link up on the screen right now that'll take you straight to our webinars. You can visit that link and view our archived webinars. And I'd also encourage folks to consider signing up for our upcoming annual meeting and conference, which will be held June 17th to the 19th in Sarnia, Lambton County Ontario. So we hope to see a lot of folks there where we'll be exploring many of these issues in more detail and in person too, which is always great. So thank you again to all the panelists. Really enjoyed working on this project with everyone, and thank you to all those that joined today to participate on the webinar.
Thanks, Melissa.
Thanks, guys. Bye-bye.
Thank you.